Hey guys, today we're going to talk about the Dinitz problem. This problem was first conjectured by Jeff Dinitz in 1979 and was not solved until Fred Galvin did 15 years later. So this problem is quite difficult by any standard. But before I tell you the problem, I'd like to inform you with the goals of this video. First and most obviously, I want to present a solution to a problem I found interesting. But there are also two other goals I had in mind. The first of these is that the topic of the video, in this case the Dinitz problem, should not have been covered on any YouTube video in the past. There's so many videos on the platform that this became a bit of a challenge for me, but I think I did a pretty good job choosing a topic. And the last goal is that the solution should be presented in such a way that you, the viewer, could maybe have a little thought in your head that I could have thought of this too. And with no doubt, this is an extremely hard problem and comes with a pretty unmotivated solution. But I still hope that you follow along and that there are no parts that baffle you, because only then have I truly succeeded. So let's get started. Let's say we have a square grid, in this case a 3 by 3 one. Now we assign each square the amount of colors equal to the size of the grid. Here the grid is of size 3, so I've chosen 3 colors for each square. Now I highly encourage you to pause the video and try to choose one color for each square, such that every row and every column contains different colors. For example, there shouldn't be a row that contains 2 red squares. Okay, so here's a possible answer. There are many other answers as well, so the majority of you should have gotten a different one. I'm assuming that unless you got lucky, some trial and error was required to find one. It took me a bit too long to admit.
But our problem is in this specific case. It asks if no matter how large is the grid, no matter how we assign the colors to each square, whether such a coloring is always possible. And the answer is yes. But how should we go about solving this problem? We could try to construct a coloring given the input information, but our simple example with just a 3 by 3 grid takes such a long time to find. Generalizing a certain algorithm to all sizes and color assignments seems unfeasible. So what else can we do? The first step is already a tough one to make, but it's realizing that there's not much we can do with the grid in this problem. And especially with coloring, there's another form that's much more natural. Now this is a pretty big leap to make, but consider each row as a dot or a vertex on a graph. Now do the same for the columns. Now notice the intersection between a row and a column uniquely determines a square. For example, the intersection of the first row and the second column determines the square shaded in green. In our graph visualization, we can draw an edge between the dots representing the respective row and column. Again, this edge represents a square. If we draw lines between every row and every column, we get an equivalent formulation to our grid, called a complete bipartite graph, or Kn, n. It's bipartite because there are two parts, in this case the rows and the columns, and it's complete because between every vertex from the first part and every vertex from the second part, there is an edge connecting the two. Since both of the two parts of this complete bipartite graph have size 3, this is called a K3, 3. So how can the problem be restated in this graph formulation? Well, remember, the squares are the edges, and two edges are in the same row or column if they share a vertex. So we assign the edges of a Kn, n colors each, and each edge needs to be colored in such a way that no two edges that share a vertex are colored the same color. This may sound less intuitive than the problem is stated as a grid, but as you will soon see, it's much easier to work with. Actually, this type of coloring has a name. It's called list edge coloring. The least amount of colors assigned that are required for a particular graph G is noted as CH prime G, where CH stands for choice, and the prime means that we are coloring edges and not vertices. So we have to prove that CH prime of Kn, n is less than or equal to n. To not distract from the flow of the video, and to check for understanding, I will ask you, the viewer, to prove that at least n colors are required. In other words, CH prime of Kn, n is greater than or equal to n. By giving an example of an assignment of n minus 1 colors to each edge, where it is impossible to choose a working coloring.
Okay, so now how can we attack this problem? Let's focus on a much more general question. Given a graph G, how can we find upper bounds on the choice number CH of G? Note here that we are coloring the vertices, not the edges, hence the lack of the prime in CH of G. Two vertices are adjacent if they are connected by an edge. We will first compare list coloring to regular coloring. In regular coloring, we don't assign the vertices any colors to choose from. All we do is give each vertex a color such that no two adjacent vertices are the same color. The chromatic number chi of G is the minimum number of colors required to do this. Finding an upper bound for chi of G is quite easy. All we do is give an example for a coloring. But finding a lower bound is difficult. How will we prove that a coloring exists using some number of colors, without going through all the cases? On the other hand, for list coloring, lower bounds are about as hard as a lower bound for regular coloring, since all you have to do is apply an assignment of colors, and then prove that no choices from the assignment create a working coloring. If you actually paused the video and did the previous exercise, you just created a lower bound for a list coloring. But an upper bound for list coloring is much more difficult, since we need to prove that for all possible lists, a coloring exists. So how might we approach this? Well, a good start would be to examine methods for finding tight upper bounds of regular coloring. One of the simplest is called the greedy algorithm. It works as a method to find a coloring with a small amount of colors, though it can't always guarantee the smallest. Suppose that we have a graph like this one. First, we order a bunch of colors, enough so that we won't run out when coloring the graph. I have ordered them as red, orange, yellow, green, blue, and finally purple. Then we number the vertices in any order we please. I would just do it in clockwise order, starting with this one. Now all we do is go through each vertex, one by one, and color it with the first available color. Let's use this graph as an example. The first vertex has no restrictions, so it's colored red. The next vertex, vertex 2, is adjacent to vertex 1, so it can't be colored red. The next available color is orange. Vertex 3 is adjacent to both vertices 1 and 2, so it should be colored yellow, the first available color. Vertex 4 is not adjacent to vertex 1, so it can safely be colored red. We can keep going and eventually come up with this coloring that only uses 4 colors. Okay, so now we know what the greedy algorithm is. How can we find the number of colors it returns? Or at the very least, an upper bound, without going through the whole algorithm. One method is by orienting every edge so that it points towards the smaller vertex number. What we have now created is called a directed graph, since every edge has a direction. And now what our algorithm does is goes through every vertex in order, looks at all the vertices that given vertex points towards, and chooses the first color such that none of the vertices that were pointed towards are colored this color. And right now you're probably thinking, okay, but what does this accomplish? Well, look at a particular vertex V. Suppose it's pointing to k vertices. We call k the out degree of V. Okay, so the out degree of V is k. In this specific case, 2. The worst case scenario is if all of these k vertices were colored differently. Then V has to be colored with the color different from all of these k colors. But this means that no matter what, at most k plus 1 colors are used. We can do this for all vertices, which means that the number of colors used is at most the maximum out degree of a vertex plus 1. In mathematical notation, we have just proved that chi of G is less than or equal to the maximum value of d plus of V, which is the out degree of V, plus 1 over all vertices of the vertex set of G, denoted as V of G. We have now answered our question about finding an upper bound on the number of colors the greedy algorithm uses, but we're not quite done yet.
Let's go back to our colored graph and look at the vertices colored with the color 1, in this case red. One trivial property of the red vertices is that they form an independent set, which means that there are no edges between any two of the vertices. This is obvious because otherwise they couldn't be colored with the same color. But there's also a less obvious property, and that is that every other vertex must point to at least one red vertex. Because if a vertex didn't point to at least one red vertex, it should have been colored red instead, due to the red being the first color in the color order. So we have proved two properties of the vertices that are colored red. Surprisingly, with these two properties, we're able to prove the same thing we did previously. just in a much more convoluted manner. We use induction. Again, what we're trying to prove is that the greedy algorithm generates a coloring that uses at most the maximum out degree plus 1 colors. The base case is a bunch of vertices with no edges. Here the maximum out degree is 0 and 1 color is used. For the induction step, consider a graph and apply the greedy algorithm on it, as shown. Suppose the maximum out degree is k. We want to show that at most k plus 1 colors are used. Consider the set of all vertices that are colored with the color 1. Here it is red. Now remove these vertices from the graph and all the edges that are associated with these vertices. From one of our properties, every remaining vertex pointed to at least one of the red vertices, so every vertex lost at least 1 out degree. Therefore, the maximum out degree is at most k minus 1. So at most k colors are left in the remaining graph by the induction hypothesis. Adding back the red vertices, we have at most k plus 1 colors, which completes the proof.
Now you must be thinking, we already proved this. Why do we need to prove it again in such a complicated way using induction? Well, the reason is that it generalizes to list coloring as well. Define a kernel on an arbitrary directed graph, which doesn't need to be formed by greedy coloring, to be a set of vertices that satisfy those two properties. Look at this graph and try to find a kernel. Okay, the answer is that the red vertices form a kernel, because they're an independent set, and every other vertex points to at least one red vertex. Now the lemma that we're going to prove is stated as the following. Consider a graph, and for each vertex of this graph, we assign a list of colors. These lists don't have to be the same size, contrary to what we've discussed about list coloring in the past. For this graph, we're given that there exists an orientation that satisfies the following properties. For every vertex, the size of the list assigned to that vertex is at least the out degree of that vertex plus 1, and that every induced subgraph has a kernel. Here, an induced subgraph is just a graph formed by the subset of the vertices of the graph. And these two properties are not really anything special. They're simply the two things we talked about previously, adapted to the environment of list coloring. By assuming that this graph has an orientation that satisfies these two properties, we can prove that the graph can be colored using the given list, and the proof is basically the same. Again, we use induction. The base case is a bunch of vertices with no edges, which can easily be proved to work. For our induction step, consider the induced subgraph formed from the vertices of the graph that contain a certain color. We have chosen red. By assumption, there is a kernel in the subgraph. Let's remove the vertices of this kernel and all edges associated with these vertices. By the definition of a kernel, every other vertex in the subgraph, in other words, every other vertex with red in its list, loses at least 1 out degree. We then remove all the red from the list of the remaining vertices. However, since the vertices that had red lost an out degree, they will still satisfy the property that the size of the list is at least the out degree plus 1. So the remaining graph satisfies the first property. And it obviously satisfies the second property as well, since the subgraph of the remaining graph is a subgraph of the original as well, and thus has a kernel. This means that we can use the induction hypothesis, and assume that the remaining graph can be colored using the remaining list. Adding back the kernel, we can simply color all the vertices red. Since a kernel must be an independent set, there are no conflicts, which means that we have successfully proved that the graph can be colored using the list.
Okay, that was exhausting, but we're not quite done yet. Let's go back to our complete bipartite graph Kn, n. Remember, we're trying to prove that the edges of this graph is list colorable with n colors, where edges are adjacent if they share a vertex. In other words, we want to prove that ch prime of Kn, n is less than or equal to n. However, this is not any different from vertex list coloring at all, it's just in a different skin. We can treat these edges as vertices and apply our theorem to the resulting graph. If we can find an orientation where each edge has an out degree of at most n minus 1, and where every induced subgraph has a kernel, we would be done. Before we begin to prove this, let's first generalize to general bipartite graphs. Let G be a bipartite graph. We will prove that ch prime of G is less than or equal to chi prime of G, or if you still remember, chi is a regular chromatic number, the minimum number of colors needed to color a graph normally. Since normal coloring is just list coloring where all the lists are equal, we obviously have ch prime of G is greater than or equal to chi prime of G. This means that we will then prove that ch prime of g is equal to chi prime of g, even though equality isn't necessary for our problem. To do this, we need to find an orientation that satisfies these two properties. And the first is that each edge of our bipartite graph has an outdegree of at most chi prime of g minus 1, and the second is that every induced subgraph has a kernel. Let's focus on the first condition. The outdegree of a vertex seems little related to coloring, so we suspect our orientation should be related to coloring. For simplicity purposes, let chi prime of g equal to n, and let's color our graph with n colors. Suppose our order is red, green, blue, and a certain edge is colored with color k, in this case green or color 2. To describe our possible strategies, let's call the parts of our graph A and B. One possible strategy is to add an outdegree for all edges that are adjacent to our green edge E, if and only if they are adjacent in A. Since all edges adjacent in A have different colors, there must be at most n minus 1 edges adjacent to E and A, which creates an outdegree of at most n minus 1. This does seem to work, however it creates the following problem. Consider two edges adjacent in A. Which direction should the edge connecting these two edges point? By our definition, it must point away from both edges, which is absurd. So clearly we need to try a different strategy. After some trial and error, we may stumble upon the following strategy. Let's say our edge E is adjacent to another edge in A. Then E points to the other edge if and only if the other edge is of a lesser color. This means that E points to at most k minus 1 edges, since at most one edge of each color less than k is being pointed to. And the opposite is true in B. If E is adjacent to another edge in B, then E points to the other edge if and only if the edge is of a greater color. Since every color from k plus 1 to n is being pointed to at most once, this means that E points to at most n minus k of these edges. So the outdegree is a sum of k minus 1 and n minus k, which is n minus 1, which is what we wanted. And this also creates no contradictory statements, due to the fact that from two colors, one color is less than the other. So now to complete our proof, all we have to do is show that with this orientation, every induced subgraph has a kernel. And by induction, it only suffices to prove that the whole graph has a kernel.
Now, how will we approach this? It seems like a tough task to prove for all colorings in bipartite graphs in general. But we might notice that due to the nature of the orientation we chose, specifically transitivity, we can express the arrows much more simply as preference. Suppose that there is a vertex V, and it's adjacent to vertices A and B, where the edge connecting V and A points to the edge connecting V and B. Now we can simply take this as meaning that B is preferred to V over A. And I will ask you to check that due to how our orientation was set up, there is no contradictory information, such as A is preferred over B is preferred over C, and C is preferred over A. For further ease of understanding, we will take the vertices from set A as men and vertices from set B as women. So now the preference context is more apparent. And we're looking for a kernel, right? Well, a kernel is an independent set of edges, which in our new context is simply a set of possible relationships. And the second condition is that every other edge points to an edge in the kernel. What this can be interpreted as is that the marriages are stable. In other words, no other set of marriages would be completely preferred over our kernel. So basically we need to prove that a stable set of marriages exist. This is the stable marriage theorem, one of the most famous and applicable theorems in all of graph theory. To prove it, we'll construct such a matching as follows. Remember that the color order is red, green, blue. The vertices in A prefer smaller colors, and the vertices in B prefer larger colors. We'll start with an empty set of edges. Now take a random vertex in A. Here I just took the top vertex and connect it to its preferred vertex in B, which is through the red edge. Now we go to the next vertex and do the same. But when we get to the third vertex, its preferred vertex is already taken by the second vertex. When this happens, we let the vertex in B choose what it wants. Here it would rather have the vertex along the blue edge. So we scrap the red edge and let the second vertex choose its next favorite, along the green edge. Finally, we go to the last vertex. It can't be with the red edge, since the vertex in B prefers the green edge. And it can't be with the green edge, since the opposing vertex is connected to a blue edge. So it resorts to its last choice, the blue edge. Once this algorithm is finished, which you can check that it always does, the resulting matching is actually stable. If it wasn't, There must be an edge that creates instability, an edge such that both its ends prefer it compared to its current partners. We showed that this is impossible. To see why, we considered two cases. If an edge was not adjacent to any edge in our matching in A, then because our algorithm has ended, it must not be preferred over the adjacent edge in B. And secondly, suppose that there was an edge that was adjacent to an edge in our matching in A and is preferred over the edge in our matching. Then it must not be preferred by the adjacent edge in B, by how our algorithm was constructed, because otherwise it would have been chosen by A. So that means we're done. If you still remember, the original problem was just about grids. But throughout this video, I've taken you through a tour around several parts of graph theory, from list coloring to the greedy algorithm to kernels, and finally the stable marriage theorem. I hope you were able to follow along, and if you enjoyed the video, I would really appreciate it if you could show some sign of life, either by liking the video or leaving a comment. And one last thing, this video was made for 3 Blue 1 Brown Summer of Math Exposition. If it wasn't for him, this video almost surely wouldn't have been created, so special thanks for giving me the motivation to create it. And if you were also a part of the Summer of Math Exposition, please consider giving a positive peer review, it means a lot to me. If this video gets positive feedback, I may consider making another one in the future. Thank you, and I hope to see you again.